Okay, good day. This is dual enrollment pre-calculus. I am Mr. McCulley. This is lesson 13, properties of logarithms. Let's get right to it. So today we are going to be rewriting logarithmic functions with different bases. We're going to use properties of logarithms to evaluate and rewrite logarithmic expressions. And we're going to use properties of logarithms to expand or condense logarithmic expressions. And then finally, we're going to use logarithmic functions to model and solve problems. And what are the properties that we're going to be using today? Well, these are our properties that we will be using today. And so basically, these first two will be most useful in calculus when we start doing derivatives, but that's a little ways away. It's also, since we're talking about logarithms, a good chance to introduce these properties, and then hopefully when we get to it, calculus, you'll remember them or at least have an idea. But basically what it says, if you have a logarithm of a product of two different values, and these values could both be expressions, you can expand those two, or that logarithm, into a product of logarithms of the same base. And if you have the logarithm of a quotient of two expressions or two values, you can expand that into a difference of two logarithms of the same base. Now this third one that says that if you have the logarithm of an exponential, you can bring that exponential down in front and have the logarithm of just that value. And that's just an expansion of this first property. But what it's very useful for is solving for unknown variables that are the exponentials. So when I started way back at the beginning and I said solving this equation is a little bit tougher, it's at 2, we're going to use this property here to solve this expression and get a nice number that we can use. So first thing we're going to talk about is deriving the change of base formula, and the change of base formula basically says this. If I wanted to figure out what the log base 3 of 7 was, how can I calculate that? And I want to know what this value is, and for right now we're just going to call it y. But keep in mind a couple of things. First, we know, and I put this in quotes, two logarithms. And so if I grab my graphing calculator, I have two logarithms right there on my graphing calculator. I have log log base 10, and I have ln log base e. So I know any of those values. I can say, if I wanted to say what is the ln of 7, I could just type that in my calculator and calculate it. All right, so we can do that. We also can change logarithmic form to exponential form. All right, and so we did that in the last lesson. So let's start with this. If I want to figure out what log base 3 of 7 is, and I say let's set that equal to y, first thing we're going to go, we're just going to copy it again, log base 3 of 7 equal to y, and I'm going to say change this to exponential form. All right, so I can do that. 3 to the y equal to 7. Okay, so using the properties and rules of algebra, we can take a known logarithm of both sides. All right, so properties of algebra say if you do the same thing to both sides of the equation stays in balance. And so I'm going to use ln just for this instance, but please know that I said it's a known logarithm. You can use whichever one you want. All right, so I'll go 3 to y equal the ln of 7. And now we're going to use property 3 to bring the exponent down. So if we go back to this previous slide, maybe it'll go back to the previous slide. Since I have the logarithm of an exponential, I can bring that exponential down. So we want to do that. And so I'll have y times the ln of 3 equals the ln of 7. Now both the ln of 3 and the ln of 7 are calculable values. You can put it into your calculator. All right, and since it's a calculable value, I know that it is a known quantity. So we can, since it's a multiplication, just divide both sides the ln of 3. And we'll get y equals the ln of 7 over the ln of 3. Now, because I can use my calculator to calculate both of these two values, we're essentially done. And so I can go to my graphing calculator and I can say that the ln of 7, close this value, divided by the ln of 3, close that value, hit equals, and I get 1.771. All right, and that's what we're trying to find. So log base 3 of 7 equals 1.771. Now we can test that because we said that y was also equal to this thing. So if I took 3 and I raised it to the previous answer, this value here, I should get 7. That's what we should get, and we see that clearly we do. So we're fairly good on this. Now what this allows us to do is we can generalize to the change of base formula. And so if I'm trying to evaluate log base A of x, I can do any of these three equivalencies as long as I know what the base is. And so since I know what log base 10 is, if I wanted to, I could say log of x divided by the log of a. If I wanted to do use natural logarithm, I can, or any other known logarithm. Okay, and so this is just a generalization of these two specific forms. All right, let's talk about some examples. That's all really the new stuff. So examples. Oh, I thought I had written these out. Sorry about that. So we're going to call an audible and pull these back. Oh, I remember. This was section 3 point properties. These are pretty short ones. These are fairly simple. So the first one says rewrite the logarithm as a ratio of common logarithms and natural logarithms. And so remember, the common logarithm is log base 10 and the natural logarithm is log base e. So when they ask us in number 6 to take log base 3 of x, and we can rewrite that as an a would be common logarithm. So log x over log 3, and natural logarithm for part B would be ln x over the ln of 3, and that's it. Number 14, it says evaluate the logarithm using the change of base formula. Round your result to 3 decimal places. And so in number 14, they give us log base log base 9 of 4. So we're just going to use the same thing we did here. We'll go log of 4 over the log of 9. We'll grab our graphing calculator. Log 4, oops, make sure we close that up, divided by the log of 9, close that up. Excuse me. Hit enter and we get this 0.631 because we have to round to 3 decimal places. But I also want to show you ln of 4 real quick here divided by the ln of 9. Using the change of base formula, these two things should be equivalent, and we clearly see that they are. And so this solution 0.631 after we do our rounding. In number 40, the question asks us to simplify the logarithmic expression. So we have this log base 3 of 9 to the second, and then they multiply that by 2 to the fourth. Okay, so we have this 2 to the fourth. Let's focus on this expression first before we do anything. And the reason that I'm going to do it this way is because I know that if I have a property of logarithm from the last one, log base a of a to the x was just x. Log base 3, 9 and 3 are perfect powers of 3, are both perfect powers of 3. And so I know that since 9 is 3 squared, I'm going to go log base 3 of 3 squared times 2 to the fourth. Let's do that better because that looks almost like a 24. Let's make sure we have that as an exponent. Okay. All right. And this should also be squared because 3 squared is 9, and then we still have a square there. And so here we're going to say a to the x to the y is equal to a to the xy. That'll give me log base 3 of 3 to the 4th times 2 to the 4th. And so I'm going to bring this exponent down. So using that property 3 where it's log base a of x to the n equals n log base a of x. Bring that exponent down in front, and so we'll have 4 log base 3 of 3 times 2 to the 4th. And so I'm going to do two things here. Remember that log base a of a is equal to 1, and that 4 is 2 squared is equal to 1, and 4 equals 2 squared. So I get 2 squared, put it to the third, 2 squared times 1 times 2 to the 4th. And remember, a to the x times a to the y is equal to a to the x plus y. And so we just have 2 to the 6th, since 2 plus 4 is 6, and that's simplified. All right, let's move on. Maybe. Not quite sure why this isn't changing. There we go. Some examples. Use the properties of logarithms to expand this expression as a sum, difference, or constant multiple of logarithms. So basically, we're just going to use these properties that we had in the first slide here. Maybe. There we go. And so we're going to use these properties to expand. And so the first thing, we have a product here. So we have the product of two expressions. And so we're going to expand this to log base 2 of x squared plus log base 2 of y to the third. So since I had a product between x squared and y squared, I can expand that to a sum of two logarithms with the same base. Now, because they both have exponents, and they say as a constant multiple of logarithms, we can bring those exponents down and make them multiples of log base 2 of x and log base 2 of y. And so we get 2 log base 2 of x plus 3 log base 2 of y. Now we could do a similar expression with this one, but before we do that, I'm going to do one more step, and I'm going to say change your radical into a rational exponent. So we're going to rewrite this as log base 4 of x to the 1/2, the same as square root over x to the 4th, or excuse me, y to the 4th. Let's make sure we do that correctly. This is log base 4 y to the 4th power. Okay, now because it's a quotient instead of a product, we can expand this with a difference. So log base 4 of x to the 1/2 minus log base 4 of y to the 4th. And just like we finished up with the last one, we're going to take those exponents and bring them down. So we're going to go half log base 4 of x minus 4 log base 4 of y. And that will be our final answer for that one. Now in the next section, they ask us to condense. Now remember, we expanded with the product and the quotient first, and then we brought the exponents down. So when they ask us to condense in the next one, we're going to bring those multiples up first and then combine them. So this one, the first thing I want to do is I want to take those exponents that are those values, those constant multiples, and move them up to exponents. That'll give me the ln of x squared minus the ln of y to the 4th. And because we have a difference here, a subtraction, we can combine that into a quotient of a single logarithm, ln of x squared over y to the 4th. And just for good measure, we have make it as an put parentheses around that. Now, in all the other ones that we've done so far, we've condensed with just single variable values. Here we have an algebraic expression, but we still treat it as the same thing. We have a sum here, so I can combine those with the product. And so this becomes just a common logarithm of x plus 1 times x minus 2. And we can simplify that just a little bit because these are two binomial expressions that are being multiplied. So we can just FOIL and go log of x squared. X times negative 2 would be negative 2x, and 1 times x is positive 1x, plus the negative 2x gives me negative x. And then positive 1 times negative 2 is negative 2. And that will be our final answer. All right, so let's evaluate some logarithms without using a calculator. And these are my last two. And so for this first one, for us to do it without a calculator, we know some things. These calculations have to be fairly simple, and they have to, for the most part, include some whole numbers, or in this case, fractions of whole numbers that we can calculate. So since I have log base 3, and I'm asked to evaluate what this thing is, I'm going to say, let's let that equal to y for right now. All right, when we figure out what y is, we're going to be okay. So I'm going to say, recall that 81 is 3 to the 4th, okay? And so if it's 3 to the 4th, we can say that this thing right here would be log base 3 of 3 to the 4th equal to y. And so now I'm going to say change to exponential form. Why? Because if I change this to exponential form, and this is a 4, I get 3 to the y equaling 3 to the 4. Now this thing becomes very easy to solve. Since the bases are the same, the exponents have to be the same. Y equal to 4, that's what we're trying to evaluate, find for y, so we know that we're done. Now for this one, we're going to do the same thing. We're going to set it equal to y just for a moment. But in this one, I'm going to say, recall that a to the negative x is equal to 1 over a to the positive x, and that 125 is 5 to the 3rd. Now it has to be, again, I have this base of 5. We're trying to evaluate some of this stuff without using a calculator. So the first thing I want to do is let's use that property and rewrite. So let's go log base 5 of 125 to the negative 1 equaling to y. Then in my next step here, I'm going to use this 125 is 3 to the 5. So I've got log base 5 of 3, excuse me, it would be log base 5 of 5 to the 3rd, all to the negative 1 property, because 5 to the 3rd is 125 and it still has that negative 1 equaling to y. And so here we can use a to the x to the y equaling a to the xy, and that'll give me log base 5 of 5 to the negative 3rd equaling to y. And so change the exponential form just like we did in the last one. 5 to the y equals 5 to the negative 3. Therefore, we can conclude that y equals to negative 3 and be done. And that's all I have for today, folks. So, the super Star Wars fun fact of the day. George Lucas' first choice of voice was Darth Vader, Orson Welles. Orson Welles was very famous back in the 70s. He did some wine commercials. But he thought that the deep resonating voice of Orson Welles would be too recognizable, so he set on this younger man, James Earl Jones, who's become the iconic voice of both Darth Vader and CNN. Well, that's all I got for today, folks. Have a good one. Goodbye.